Hi, so we're back, moving back to chapter 6. And in chapter 6, we talked about exponent rules. And we skipped over section 6.2 because there's really a lot to it. And we want to make sure you have the background knowledge for it. So we're taking 6.2 and we're kind of making it its own chapter to really delve in to the background knowledge that you need to be able to really understand the basics and the complexities of section 6.2. So we're going to go ahead and start with 6.2a, the very first part that you need to know, and that is simplifying radicals. Now, a lot of people ask me what a radical is, and a radical is like a square root. That's a radical. And then we have a cubed root and a fourth root. So those root signs are, so the square root really doesn't have the 2 because it appears so often. We don't always write that 2, so I can really undo that 2 if I wanted to. Now, when we simplify radicals, what we do is we simplify radicals instead of turning them into decimals. We don't want to turn them into decimals. And the reason why we do that is because we want to keep something in what we call its exact form. An exact form is really important because it can eliminate rounding errors that occur when you make calculations. So for a very, very simplified example, the number square root of 2 is really 1.14213562. Now, if I multiply 1,000 times the square root of 2, I'm going to get this number, 1,414.213562. But if I take the square root of 2 and I round it to 1.4, and then I times it by 1,000, I'm going to get a value of 1,400, which actually has a rounding error of 14.213562, which when you talk about money, I'd rather have an extra $14.21 rather than not. But the main idea here is that when we make calculations with a rounded decimal, our rounding errors will compound with each calculation we make. And this has the possibility of being disastrous. And disastrous because where do we usually use math the most? We use it in engineering. We use it for buildings that need to withstand earthquakes, buildings that need to withstand tornadoes, airplanes that need to stay whole in the air when they get hit by lightning and all this sort of stuff. All this mathematical calculation that goes into engineering and developing things with safety in mind. And so a lot of people are like, oh, exact form, who cares? What's the big deal about rounding? Well, you want people to be using exact form. You want people to be using good math. You don't want people to be making tiny little mistakes when it comes to your life or your loved one's life being on the line. And so ultimately, everything that we do mathematically in the real world has big importance. And so we want to make sure we're doing that accurately and responsibly. So how do we simplify radicals? There is something called the product rule of radicals. So let's go ahead. That's the product rule of radicals. And we're going to use the product rule of radicals. And the product rule of radicals that says when you multiply two radicals, so the square root of a to the square root of b, you can actually multiply those numbers on the inside, also known as the radicands, and combine them underneath one square root. What's cool is that the opposite is also true. If you have two numbers on the inside being multiplied, I can separate that out. So we're going to use that idea to simplify a radical. And so the first method we're going to use is really the perfect square method. So we're going to go ahead and we're going to highlight these, oops, I need the highlighter again, these perfect squares. And so what we're going to do is we're going to take a look at our numbers, and it's usually easier with small numbers, harder with the bigger numbers we get, to find the biggest perfect square that can be inside or be divided by the radicand. That is a factor of the radicand. So here my radicand is 8. So I want to look at my perfect squares and figure out what's the biggest number that can go into 8. And so I would see 4. So 8 is really the same thing as 4 times 2. Now I can use that product rule and break up that square root, square root of 4 times the square root of 2. Now keep in mind, this only works for multiplication. It does not work for addition. Only multiplication, not addition. And then I could go ahead and simplify. Well, what is the square root of 4? So what number times itself gives me 4? Well, that's 2. So this is really 2 square roots of 2. And so then I can move on and try another problem. So 32. So what's the biggest number in my green list up here that can go into 32? So 4 can go into 32, 9 can't, but 16 can go into 32, 25 can't. So 16 is the biggest number, so 16 times 2 gives me 32. So then I can break that up, square root of 16 times the square root of 2. And the square root of 16 is really 4, so this is 4 square roots of 2. And then I could move on to the next one, 75. So the biggest perfect square that goes in there is 25. So 75 is really 25 times 3, which is really the square root of 25 times the square root of 3, which is really 5 square roots of 3. And so that's just simplifying our radicals. And to be able to do this, once we do this, we have certain rules that we could do to work with that. So now when we multiply stuff, we can talk about how to multiply correctly and keep this in exact form instead of a rounded decimal. Okay, so another method for simplifying radicals. So some people, they can look all they want in a number and they don't know what perfect square goes into it. They're not that good at dividing, so they have a hard time with that. So we're going to use another method called prime factorization. So with prime factorization, we're looking at trying to divide our number into all the prime numbers that go into it. So prime numbers would be, oops, let's undo that. So prime numbers would be 2 is our smallest prime number, and then 3, and then 5, and then 7. 9's not prime, but 11, and 13, and 15's not, but 17 is, and 19 is, and 21's not, 23 is, 25's not, 27's not, but 29 is, and 31, and so on and so forth. And the list of primes goes on for a long time, but really we're looking at these numbers. And so the idea here is that if we can break it down to its primes, we can then look for bits and pieces. So we use the idea of inverse operations. For example, the opposite of square root is squared. So if I have the square root of 2 squared, these should cancel each other out. Or if I have the square root of 3 squared, they cancel each other out. And so 2 squared is really just 2 2's. 3 squared is really 2 3's. And so the idea is that if I have a pair of them, that's going to give me a squared. It comes outside as just one regular number because of that canceling of the squared and square root. Now it doesn't only work with the square roots, it works with cubed roots. So if I have the cubed root of 2 to the third, the cubed root and the third power will cancel out, giving me the number 2. So then when I'm looking at breaking down into primes, 2 to the third is really 3 2's. So as long as I have 3 2's, that will cancel out and give me just 1 2 on the outside. And so we're going to use this idea to help us out. So we have 2 different ways to break down a number into primes. So here I have the square root of 180. I can do the tree method. So I could say 180 is 18 and 10. I break down 18 into 3 and 6. I break down 6 into 2 and 3, and so on and so forth. And then we have the reverse division method. Now I've talked to you about this prime factorization before. We've seen this, so it shouldn't be new. Reverse division takes the smallest prime number, usually a 2, and you keep dividing by 2 until you can't anymore. So 2 goes into 180 90 times. So then 2 goes into 90 45 times. Now 2 can't go into 45, so we go to our next prime number, 3. So 3 goes into 45 15 times, and 3 goes into 15 5 times. Once we get to our last number and it's prime, we're done. So we get to a number and it's prime, we stop, I don't put a box around it, we're done. And then here's a list of all of our primes, which is really nice because then I can say, well, this is a square root, So I'm looking for two of the same factors. So I've got two 2's, which means I get a 2 on the outside. I've got two 3's, so I get a 3 on the outside. This does not have a pair, so it can't undo the square root, so it stays on the inside. And this gives me an answer of 6 root 5. And down here, it really breaks into more. Here I've got the 2, 2, 3, 3, and 2 times 2 is really 2 squared. Those cancel out. Square root cancels out the squared. But we tend to shortcut these. So let's go ahead and work through some examples together. So these are pre-worked out for us. Let's see what it looks like on our part. So again, it's up to you to use a tree or reverse division. I like reverse division because it just looks nicer. So I'm going to go ahead and break down 48. I'm going to use my smallest prime number, which is 2. So 2 goes into 48 24 times. And then 2 goes into 24 12 times. And 2 goes into 12 6 times. And 2 goes into 6 3 times. Since 3 is prime, I stop there. And now, because this is a square root, I'm looking for pairs, so groups of 2. If it was a cubed root, I'd look for groups of 3. And so now I'm going to go ahead. Okay, I've got one group of 2's, so I get a 2 on the outside. I get another group of 2's, so I get another 2 on the outside. And then I have a 3. There's no pair, so it can't undo the square root, so it has to stay on the inside. So then my answer is 4 squared roots of 3. And then that's it. So next one, 98. So I'm going to go ahead and start with my lowest prime, 2. So 2 goes into 98 49 times. Okay, 2 can't go into 49, so then I try 3. No, 3 doesn't work. 5 doesn't work. 7 goes, though. So 7 goes twice. So now that I have my prime factorization, I'm done. So now I'm looking for, since it's the square root, I'm looking for groups of 2. So I've got 2 7's, which means I got a 7 on the outside. There is no other 2, so it has to stay on the inside because there's nothing else left to cancel out that square root. So now I'm going to go ahead and move to the next one, 150. So I'm going to go ahead and write that over here. 2 goes into 150 twice. 2 goes into 150 75 times. 2 does not go into 75, but 3 does. And 3 goes 25 times. And 3 doesn't go into 25, but 5 does. So now that I have all my primes, I can now go ahead and look for my doubles. So I've got 2 5's. So I get a 5 on the outside. And then 2 and 3 both don't have a pair. So they both stay on the inside. And remember, everything here is multiplication. So if it's left on the outside, it gets multiplied. If it's on the inside, it gets multiplied. So my true answer here is 5 squared root 6. And that's it for simplifying radicals that way. Now our next examples are using one of our rules, but it's using the rule backwards. So what happens when I have square root of 3 times the square root of 2? Well, because they are times, I am allowed to put them together underneath one square root, because that is my multiplication property. And so this becomes just the square root of 6. And then for the next one, I can, the square root of 5 times the square root of 5 is really the square root of 5 times 5. Since I have a pair of 5's now, this really is like the square root of 5 squared. And remember, the square root cancels out the squared to give me just the number 5. You could also look at it as a square root of 25 and then know in your head that the square root of 25 is 5. So either way you want to look at it, you can do that. And then our next one, the square root of 5 times the square root of 10 is really the square root of 5 times 10. So this is the square root of 50. And then you can break down 50 if you want. So 50 is really 2 times 25. 25 is really 5 times 5. Since I have a pair of 5's, I get a 5 on the outside. 2 does not have a pair, so it has to stay on the inside because there's nothing to cancel out that square root. And that's it. So that's what you're going to be working on in class. And so remember, this is the basics. We're just going to keep building on this. So if you're having a hard time now, it's important that you're getting help in class to really understand this before we move on.